We'll do a few past year problems. A 375 watts, 230 volt, 50 Hz capacitor start single phase induction motor has the following constants for the main and auxiliary windings at starting. So these are the main winding components and this is the auxiliary winding components. Neglecting the magnetizing branch, the value of capacitance in microfarad to be added in series with auxiliary winding to obtain maximum torque at starting is. So we have discussed the equivalent circuit only when there is a main winding. That means when the induction motor is running. At starting we did not discuss the circuit, equivalent circuit. This is because the analysis is actually quite complex for the undergraduate level. Okay, but in this question they are asking the torque, that too the maximum torque that can be obtained at starting. So this, if you remember the torque slip characteristics, if you take a single phase induction motor then it will have 0 and this is going to be the maximum torque, somewhere it is going to occur here. Now what will happen when you include an auxiliary winding with a capacitor? The starting torque is going to considerably increase, but the maximum torque is going to occur somewhere here. And once the auxiliary winding is removed, the characteristic will follow this plot. Okay, so you can see here that we are not getting maximum torque at starting itself. This is the maximum torque, right? Now the question is, what should be the value of capacitance so that this maximum torque is occurring at the starting itself? Okay, so this condition is actually very difficult to solve for the undergraduate level. So you can just remember the formula for it. To obtain maximum torque at starting, the auxiliary winding impedance angle should be equal to theta m minus 90 degrees divided by 2. So this is the condition. Okay. Usually when we use a capacitor start motor, we ensure that the angle between the auxiliary and the main field winding, it is 90 degrees. But to get the maximum starting torque, it is a different condition altogether. That is this angle. Okay. So what are you going to get here? Theta A is nothing but tan inverse of the existing reactance is given as 12.75. Now if you include a capacitance, let us say the reactance of the capacitance is Xc, then this will be the 12.75 minus Xc will be the effective reactance divided by resistance is given by 24.5. So you can write here where Xc is capacitive reactance. Okay, this is theta A. Similarly, theta m is equal to tan inverse 15.75 divided by 12.5. This you are going to get as 51.56 degrees. Okay, so therefore tan inverse 12.75 minus Xc by 24.5 is equal to 51.56 minus 90 degrees divided by 2. So you are going to get 12.75 minus Xc by 24.5 is equal to, you will get a negative value minus 0.348. Okay, you are getting a negative value because the capacitive reactance should be higher than the reactive inductive reactance. Okay, so Xc, if you calculate, you are going to get 21.29. What is Xc? It is given by 1 by omega c. So you are going to get capacitance is equal to 1 by 2 pi into the frequency in hertz, which is 50, into 21.29. So you are going to get 149.51 microfarad. The next question we have, the equivalent circuit of a single phase induction motor is shown, where the parameters are R1 is equal to R2 dash is equal to XL1 is equal to XL2 dash is equal to 12 ohm. XM is 240 ohm and S is the slip. At no load, the motor speed can be approximated to be the synchronous speed. The no load lagging power factor of the motor is dash. Okay, so this is the given equivalent circuit. Now from the given information, one particular point here is the speed can be approximated to synchronous speed. That means what? What will happen to the slip? it will become simply 0. Now what is the question asked? We should find the no load lagging power factor. Okay. So simply first we have to find out the equivalent impedance as seen through these terminals. And whatever angle you are getting, cos of that angle will give you the power factor. Right. So the condition is that S is equal to 0. So when S is equal to 0, what will be the circuit? You can redraw the equivalent circuit. This is R1. Here we have JXL1. Now since the slip is 0, what will happen to R2 dash by 2S? This will become infinite. Infinite resistance means you can consider this as open circuit. So you are going to be only left out with JXM by 2. Okay. What about here? Here when you keep S is equal to 0, you are going to get R2 dash by 4. Okay. So this is not going to be open circuited. Here it is going to exist. So you can write JXM by 2 in parallel to R2 dash by 4 and JXL2 dash by 2. Okay. So you simply have to find the equivalent impedance looking through these two terminals. Okay. So what will it be? R1 plus JXL1, or you can directly write the given values. What is R1? It is given as 12. JXL1 is given as also 12 plus JXM by 2. XM is given as 240. So J120 plus XM by 2 in parallel to R2 dash by 4, and these both are in series. So R2 dash by 4 is 12 by 4 plus J times 12 by 2. So this you are going to get 12 plus J132 plus J120 in parallel to 3 plus J6. So this if you simplify, you are going to get 138.52 angle 83.91. So now what will be the, therefore no load lagging power factor is cos of 83.91, which you are going to get 0.106.